the process for dealing with cotangent or tangent or sine, cosine, whatever trig function you're looking at, trig ratio you're looking at, is to first determine what quadrant the actual angle you're dealing with terminates in. Okay? So when I look at 495, there's maybe two approaches of the 495 you could look at. You could look completely at 495 degrees, okay? Which would be, 360 would be there, right? Okay, and then 450 would be there, right? Another 90, and then I've got to go another 45 right there, correct? Does that make sense? So that angle right there at theta that I just traced out would be 495 degrees. Okay, that's fine to deal with. There's nothing wrong with dealing with it that way, because now if that's 495 degrees, you've traveled into that quadrant 45 degrees, right? So how many more degrees do you need to go down to get there? 45. So when I draw this right triangle that we're going to want to draw pretty much every single time, I now know that angle right there is 45 degrees. Does that make sense? And that's the reference angle. That's theta bar. Okay? Now, I think it's going to be beneficial for a lot of us, just because, if I'm dealing with, say, 24 over 3, doesn't it make much more sense to deal with that as 8 instead of 24 over 3? So when I go 495, it makes a lot more sense to start reducing multiples of 360 from that and deal with that. So if I do that, I'm actually looking at cotangent of 135. Does that make sense? And that, I think, is maybe a little bit easier for us to deal with, because if I know if that's 0 degrees and I know that's 180, then 135, there's really not a whole lot of thought how many times I have to go around, and then how many more times how many partial rotations I've got to go around. Does that make sense? And I know 135 is going to be right there. Okay? It's going to be, because obviously we know that this is 90, right? So 135 is going to fall in that quadrant that is kind of segmented by that 90-degree marking and the 180-degree marking. And it just makes things a little bit easier. So, what we learn here, and what we talk about, is that the cotangent of 495 is exactly the same thing as cotangent of 135. They're coterminal angles. You remember talking about those? So everything you learn about one angle is true then for all of its possible coterminal angles. Okay? So if I take 135 and start adding 360 to that as many times as I want, let's say I add 360 to that 1,000 times. Well, that angle that I develop by doing that is going to have the same exact cotangent value as 135. Okay? So it doesn't matter. If you can reduce this thing by subtracting multiples of 360, go ahead and do that. Okay? And even if you've got a negative angle there that you don't like, maybe it's like negative 495, you can start adding multiples of 360 to get to a positive angle that you do feel maybe a little more comfortable with working with. But now we know theta here is 135. I was supposed to increase that more. 135 degrees. Okay? Now we're going to come back and we're going to say, okay, that means then whatever point I choose off of this ray, when I go straight down perpendicular to the x-axis, you're always going to go to the x-axis, and it's always the shortest distance to the x-axis, meaning that if I was to take that ray right there, okay, does it make sense to continue moving that counterclockwise to make that ray turn into the x-axis, or does it make sense to go clockwise and let it become that x-axis? And hopefully you realize it makes more sense to become the negative x-axis, right? That's a shorter, smaller angle that terminal ray would have to continue to pass through. Okay? So we've always developed that right triangle. Your right triangle, you might want to make note of this, your right triangle will always be formed with the x-axis. Okay? Every once in a while, and you might even want to write on there that's the shortest or the smallest angle towards the x-axis. Okay. I always get someone every year to do kind of something like this. I'll get this thing to go there, and then the right triangle they create is that black right triangle. Okay. You never want to do that. You always want to make that. You always want to drop a line to the x-axis, or bring a line up to the x-axis here in a second. Or sorry, third and fourth part. Okay. So that tells us then that angle right there. Okay, and essentially all we're doing here when I find that little black angle is dealing with supplementary angles from geometry, right? That supplementary angle of 135 has got to be 45. That's 45 degrees. That 45 degrees is what we refer to as our theta bar. Okay? That's our reference angle. That's what we talked about yesterday. Whenever you have a reference, a reference on an application, something you're asking, or somebody's going to ask about you, right? They're gonna contact somebody else to find out information about you. And that's what we're doing here. We're contacting theta bar to find out information about theta. Okay, that's why we call it a reference angle. The only thing that you got to pay attention, so the reference angle, so everything that I learned about 45 degrees is going to be true for theta of 135. Okay? However, the only thing that's different is the plus or minus out front. Okay? So in this case, we're interested in cotangent. Okay? Which cotangent, if you remember, is the reciprocal of tangent, right? So tangent is opposite over adjacent. So cotangent is adjacent over opposite, isn't it? Think about that way? Okay. Now, I'll show you maybe a different approach you can use here in a moment as well. You can use whichever one you want to. But in a 45-45-90 triangle, would you agree that that side right there is N? That side right there is also N. And your hypotenuse is N root 2, right? Okay. Now, those N values, eventually maybe we'll see some questions where it actually gives values to them, like 2 and 5 and 7 and stuff like that. But if it's a 45-degree angle, we don't really care what N is. Okay? Because it's going to be the same in both. When I compare them, it's always going to be, if N was 5, it's going to be 5 over 5. If N was 12, it's going to be 12 over 12. Well, if N is N, it's just N over N, right? And all of those reduce to what? Just 1. Okay? So when I look at the cotangent of 495 degrees, that is equal to the cotangent of 135 degrees, which is equal to, okay? I'm going to write this, and there's different ways you can kind of interpret this, but tangent in the second quadrant is what kind of number? It's negative, right? Okay? Because the adjacent side is negative, right? So the cotangent of 495 is the exact same thing as the cotangent of 135, which is the exact same thing as the cotangent of 45, but negative. Does that kind of make sense? And that, now, you probably maybe won't write all those down when you're doing these problems, but I want to write that and show you that whatever we learn about the cotangent of 45 is exactly the same thing as the cotangent of 135, is exactly the same thing as the cotangent of 495, if we keep the sign, the SIGN, out in front correct. In this case, it's got to be negative, right? Okay. So if you were to take your calculator, type in cotangent of 495, or type in the cotangent of 135, or type in negative cotangent of 45, they're all going to spit back the same exact number to you. They're going to spit back what to you? You know? If I take opposite, sorry, that's adjacent, divided by opposite, what's that? Of course, N over N will give me. In this case, I need negative 1. So cotangent of 495 is the same thing as negative 1. Okay? Now, your calculator doesn't have a cotangent key on it, right? So, if I do want to figure this out, make sure you're in the right mode. What mode do I need to be in here? Degrees. Okay, so I'm going to go cotangent, which cotangent is going to be 1 divided by tangent, right? That's how we've got to type it in. Type in 495, gives me that number, right? If I type in cotangent of 135, gives me the same number, right? Now, if I type in, I'm just going to type it in as cotangent of 45. Now, this is wrong because I should put a negative out in front, right? But you see why. Because if these things are going to be equal, this 1 needs to have that negative out, right? Okay. This tangent of 45 is talking about a first quadrant angle, and we know tangent in the first quadrant is positive. Well, our real angle that we're interested in is in the second quadrant, so now you just make it negative. Does that kind of make sense? Okay. I usually, and I'm not saying you can approach it this way. You can directly know that SOHCAHTOA is sine is opposite of hypotenuse. So then when you want to know what cosecant is, maybe you say it's hypotenuse over opposite. You can memorize those, right? Okay. I'm not a fan of doing that. Okay. So when I see something like cotangent of 495, and let's just do another one. So let's get a different ratio. Let's do secant of 210. Okay, secant of 210. So dealing with that picture, obviously we know the 210, hopefully, is going to be in the third quadrant, right? So that theta, 210 degrees. How big is the angle that I need to travel to get back to the x-axis? 30 degrees, right? So theta bar is that angle. So theta bar is 30 degrees. I'm going to draw this triangle in. I'm going to deal with that right triangle there. Okay, with that being 30, this would be n, this would be 2n, and this is n radical 3, right? All true facts about any right triangle, no matter where you put that right triangle, no matter how big it is, as long as it's got a 30-degree angle and a right angle in it, it's going to have that relationship with side lengths. So that's why we really don't care about n. And a lot of times, because we don't care about n, well, it's a really nice number for n to be if we don't care about it. 1. Because then it's 2, 1, and radical 3, right? And those are really easy values to work with. But regardless of that fact, we should still be able to find secant of 210. Now, I'm not a fan, like I said, I'm not a fan of dealing with secant. Okay? So what I always do when I see that the reciprocal functions are provided, I'm actually going to do all the work for its reciprocal. I want to actually find the cosine of 210. Okay? Because that makes just a little more sense to me. If I can find the cosine of 210 and I get an answer for the cosine of 210, what can I do with that answer to actually find the secant of 210? Just flip it, right? Just find the reciprocal. So cosine of 210, looking at this thing here, cosine of 210, we know the reference angle is 30 degrees. So everything I know about 30-degree angle should be true. So cosine, this thing should be equal to cosine of 30. But now cosine of 30, what quadrant is cosine of 210 terminating in? Third quadrant, right? And cosine should be what in the third quadrant? Negative. So cosine of 210 should be the exact same thing as negative cosine of 30. And if you type that in your calculator, just type in cosine 210 and hit decimal or hit enter and get decimal, right? type in negative cosine of 30, hit enter, should give you the exact same decimal, right? Now what we're interested in, you're saying, well, calculator gave me the answer, why don't I just use that? We're interested in the exact value. We're interested in what that, it's going to involve a root here. So we're interested in that. So if I look at this 30-degree angle, cosine is adjacent divided by hypotenuse, right? So it's, and this might be the reason why we like n to be 1. If I viewed n to be 1 here, it should be root 3 over 2, right? Root 3 over 2. That's the cosine of 30, but there's that negative out front, right? So cosine of 210 is the same thing as negative root 3 over 2. Okay. Now, is that my final answer? No, because I was interested in what? Secant. If I'm interested in secant, let's just flip this thing. I get negative 2 over root 3. When I rationalize that, negative 2 root 3 over 3. And that's the exact value for the secant of 210. Okay? If we type in on our calculator, now obviously we don't have a secant key, but our calculator knows that if I take the reciprocal of cosine, so 1 over cosine of 210, that's saying the exact same thing as secant of 210. Hit enter, I get that number right there, right? Okay. Now I'm going to take negative 2. Now it's a product up top, so I got to have that in parentheses. Negative 2. I guess I don't need it in parentheses. I just like it in parentheses. Divide that out. Gives me the same exact number, right? Okay. Now, we will be more comfortable later on because of the additional algebra we might do with that number. It's better written as negative 2 root 3 over 3 than it is as negative 1.1547. Because that decimal value is irrational, right? Well, both of them are irrational. But the one with the root in it is an exact irrational number, which you cannot physically write down an irrational number without some type of rounding error, right? You can't write down the exact value. Like 1/2, 1 over 2 is the exact value of that fraction, right? But 0.5 as a decimal is exact as well, correct? Okay. I can't do that with the irrational numbers. We have to round them at some point. And for some of our applications, we don't want to have that rounded value. Okay, so there needs to be an approach that leaves it as an exact value. Is that okay? All right, let's do these other ones down here. These tend to be the ones that people kind of get tripped up on the most because they are radians. Okay. And maybe you're a person that says, okay, 16 pi over 3. I'm going to take 16 pi over 3, and I'm going to do this with it. Go 16 pi over 3, multiply it by 180 over pi. We're going to get some cancellation here. We get 60, right? Pi's cancel, so now I get 16 times 60, whatever that is. Should have asked you, Jarrett. 960. Did you know that? Liar. So 960 degrees. All right. So when I'm asked sine of 16 pi over 3, it's the equivalent of being asked sine of 960. Does that kind of make sense? Okay. So maybe, because we have time, we'll approach this both ways. Okay. Let's approach it with sine of 960. Okay. Because I think maybe angle-wise, we're more comfortable degrees at this juncture, right? You agree with that? So let's do 960. Now, I don't like doing it with 960, just like the last one we did with 495, or the one, I guess the second to last one. 960 is many revolutions around, right? Okay. So let's remove 360, and that's still going to be a number above 360 degrees, right? So let's remove another value of 360 from that. So that's 720, right? Well, 960 minus 720 is going to give you what? 240. Okay? I'm going to stop there because if I subtract 360 again, it's going to give me a negative angle, and that's just as hard to work with as 960. Okay? So 240 is a better angle to deal with. So the idea here is that sine of 960 degrees is exactly the same as the sine of 240 because they are coterminal angles, right? And coterminal angles mean that the sine, the cosine, the tangent, and all the reciprocals are exactly the same. Okay? Even with the pluses and minuses out front, they're exactly the same for coterminal angles. Okay? So now I'm going to deal with the 240. I think it's a little bit easier. This is 0. This is 180 degrees. 204 says 180. And now I need to travel how many degrees to get to 240? 60, right? And I always ask that question, once I get to 180, you always ask yourself, how much further do I need to go? Because that answer to that question, how much further I need to go, is the answer to what my reference angle is. If I needed to go 60 more degrees there, right? Doesn't it mean when I stop there and go back, I need to traverse the same 60 degrees? So when I draw my right triangle here, this theta bar, which is that angle right there, is 60 degrees. Okay. So now, if I go and implant the values that I know that exist in the 30, 60, 90 triangle, and let's just say n is 1. Let's do it with that approach. N is 1. This would be 2. This would be 1. And that would be root 3, right? Okay. So now, we're dealing with the sine of 960, which we've reduced the sine of 240, which now we're saying that is going to be equal to the sine of 60, right? 60 is our reference angle, so those things should equate. However, that blue thing is off a little bit, because the blue thing, that is talking about sine being in the first quadrant, right? And the sine in the first quadrant is a positive number divided by a positive number. Right? If I put 60 degrees over here in the first quadrant, opposite would be that, hypotenuse would be that, right? Both positive numbers. Over here in the third quadrant, opposite is what kind of number? Negative. That's a negative root 3. So this thing here should have a negative in front of it. And that's kind of what those instructions above in the PDF. We're talking about 3 things yesterday. One, find the reference angle. Second one was determine, based off what all students take calculus, what that sign should be, the SIGN. And then the third one was, okay, now you use your stuff for a triangles to kind of help you evaluate. But I got sine of 60 degrees is going to be what? But if I look at this shape here, well, let's leave it. It's fine leaving it negative right now. But opposite over hypotenuse, right? So radical 3 over 2. Does that make sense? Okay. So sine of 60 is radical 3 over 2. Throwing that negative in front, I get negative radical 3 over 2. Okay, now, whether you're, because I'm writing this just to kind of maybe hopefully make a relationship and allow you to see a connection. Maybe when you're doing these, a lot of times you don't write down the sine of 960 is exactly the same as sine of 240, which is exactly the same as the opposite of sine of 60. You don't write all that stuff down. That's fine. When I do these on my own, okay, I'm writing this stuff down like this. I'm going, sine of 240. Okay, and I'll say, okay, once I develop this triangle over here, and I know it's a 30, 60, 90 triangle, I look at the 60 degree angle, and I look at these as all being positive numbers. I don't really care about their sign right now. And I do opposite divided by hypotenuse, so it's radical 3 over 2. And that's it. Okay, well, 240, that means that the sign was negative in the third quadrant, so I'm just throwing my negative sign. Does that make sense? That's what I do, right? And I think maybe the more you do these, the more you become accustomed to the process, you can kind of shorten the amount of work that you do. Okay? It's like when you guys first started solving multi-step equations, you were probably pretty deliberate in the steps that you did, right? Okay? One step at a time. But eventually, the better you got at them, if I give you guys multi-step equations, many of you are probably going to do 2, 3, 4 steps at once. And that's perfectly fine. Hopefully, we get to the point with these things that we can do that. Now, my thought is, the only way you're going to really be able to do that is to practice, right? Okay. You're struggling with this stuff. I hope you already threw out some of the assignments. We get enough examples for the class, get enough examples to help out with that. But if you're still struggling, there's so many resources on the website to provide additional examples here. Let's do this. So we now know the sine of 16 pi over 3 is negative radical 302, right? Okay. Let's do this with radians and see if we get the same result. Okay. Now radians, instead of writing 0 and 180, we're going to write 0 and pi. Instead of 360, we're going to write 2 pi, right? Okay. When we do the degrees, I don't usually write the 360 on there, but when I do radians, I always write the 2 pi on there because it just, I think it's going to be useful here as we do this. Now, what's hard when we're dealing with radians is generally speaking, your radians are going to be some kind of fraction. And it's really hard to compare 2 pi with 16 pi over 3. It's hard to compare pi with 16 pi over 3. Because comparing fractions, in order to compare fractions really easily, it's nice to have similar denominators, right? Or same denominators. Because if the denominators are the same, then the comparison is only about the numerators, right? Okay? So, instead of writing this as 2 pi, I'm going to write this as 6 pi over 3. Instead of writing this as pi, I'm going to write it as 3 pi over 3. And now because every component inside the problem has a denominator of 3, the comparison that's going to exist now is just between the 16 pi, the 3 pi, and the 6 pi. Does that make sense? You only have to compare numerators. So, if I'm looking at how big that angle is, that angle right there would have been 6 pi over 3, right? That angle would have been 12 pi over 3, right? That angle would have been 15 pi over 3. So how many more pi over 3s do I need to go? One more pi over 3. It gets me right there. Okay. Now, drawing that circle so many times like that's a pain in the butt, right? Well, if we did it in degrees, we started removing 360 from the original angle, right? Well, if I look at that thing there and that thing there, and I know that 16 pi over 3 is greater than 2 pi, I can start removing multiples of 2 pi to get that thing to be a coterminal angle that's a little bit easier to deal with. So I'm going to take sine of 16 pi over 3 and say that that is equal to the sine of 16 pi over 3 minus 6 pi over 3. So there's a reduction of one cycle around, right? But when I subtract those, I get 10 pi over 3, right? 10 pi over 3 is still bigger than 6 pi over 3. It's still bigger than 2 pi. Okay? So that means because it's bigger, there's still one more revolution that can take place. So if I subtract another 6 pi over 3, essentially subtracting 12 pi, right? 12 pi over 3. That's going to give me then sine of 4 pi over 3, right? And I like that, and I think you're going to like that, because now, is that sine of 4 pi over 3? Is 4 pi over 3 less than that? So what that tells me is my picture can be drawn that way. Not so many loops in there, right? Or rotations, okay? And it's just a little bit easier to deal with. So when we are asked to do, when we change it to sine of 960 degrees, we converted that to sine of 240 degrees, right? Well, if I take 4 pi over 3 and convert that, it's 240 degrees. Okay? Multiply by 180 over pi, and you're going to see you get 240. All right, so that's theta. Theta is 4 pi over 3. Now, what I like about using radians here, and the reason I wrote that pi is 3 pi over 3. I'm at 3 pi over 3. How many more radians do I need to move that ray back up to the positive x-axis? Pi over 3. So that tells me that this angle right here, which we call theta bar, is pi over 3 radians. We get that right in. Okay. Now, this is something that you guys are going to want to maybe commit to memory. And there's going to be, guys, there's going to be a better approach to this later on, that we don't necessarily always draw in the right triangle. These right triangles are going to lead to something called the unit circle. You've heard that word before? Okay. The unit circle, and maybe I'll show you a picture here in a moment of what the unit circle is. But it essentially is a tool, it's a graphic organizer for all of these values that we're getting back as radical 3 over 2, 1/2, radical 3 over 3, those kinds of things. So we will eventually draw all these triangles in, but right now it's kind of a necessity. So pi over 3, you might want to make the link that pi over 3 is exactly as how many degrees? 60. So that is a 30, 60, 90 triangle. So a pi over a 30, 60, 90 triangle, let's write this way, 30, if I write it in degrees, a 30, 60, 90 right triangle is exactly the same thing as a pi over 6, pi over 3, pi over 2 right triangle in radians. Okay? So when I see those three numbers, 30, 60, 90, maybe I relate pi over 6, pi over 3, pi over 2. It's going to help us process a little bit. Across from 60 degrees is always your radical 3 side. Across from your 90 is always your 2 side. And across from 30 is always your 1 side. So now if I want sine of 4 pi over 3, I'm going to reference what sine of pi over 3 is. Okay? Referencing sine of pi over 3 would be opposite of our hypotenuse, right? Radical 3 over 2. But what is that radical 3 really going to be in this picture? It's going to be negative. The sine is in the third quadrant. So that's it. Sometimes you'll see, it's a way of organizing your work. Sometimes if I'm looking at this thing here, and I've got that angle, and I know that theta bar is 60 degrees, sometimes people will come back and say, okay, let's put that 60 degrees over here and put it in the first quadrant. And if I have a 60-degree angle in the first quadrant, I call that radical 3, I call that 2, I call that 1. And now I say, okay, what is the sine, cosine, tangent, or whatever of that 60 degrees, right? So if I'm doing this one, sine of 60 degrees is equal to radical 3 over 2. So then when I go back to this picture here, the sine of 240 is going to be the exact same thing as the sine of 60. The sine of 240 is going to be in what quadrant? Third quadrant. So then they go back through and they say, okay, well, that's negative. Okay? And now we have the sine of 240 is equal to negative root 3 over 2. Okay? So sometimes people will take out, I always draw it in because it does work, but some people, once they find the reference angle, they will redraw a quick coordinate plane, put that reference angle in the first quadrant, learn everything you know about that reference angle, find the sine, cosine, tangent, whatever they want about it, and then go say, okay, now what was I really looking for? I was looking for 240, and that should be in the third quadrant, so that makes the plus or minus sign, in this case, a minus. Is that okay? I know maybe initially there's a lot of like new processes here and a lot of things that we're kind of wrapping together, like coterminal angles, supplementary angles, that kind of stuff, and dealing with multiple rotations, and maybe these three processes or three steps can be confusing. But again, the more practice I think we see, the better we'll get at it. The secant here, negative pi over 4, secant of negative pi over 4. Like I said, I'm a fan of not dealing with secant. I'm going to deal with its reciprocal. I'm going to deal with the negative cosine of negative pi over 4. And then I'm going to remind myself when I'm done, I've got to take whatever I find out to be the cosine of negative pi over 4, I got to take the reciprocal of that, right? And that's going to be my real answer for the secant of negative pi over 4. So The negative pi over 4, if you remember what we talked about in section 5.1 when we first introduced how we deal with angles. A negative angle is simply just talking about the rotation direction. Okay? So if I have my initial ray here, a positive angle means that that initial ray starts to move counterclockwise, right? A negative angle means that that ray moves that direction. So that would be negative pi over 4. Is that okay there, everyone? Okay. So if theta here, that theta is equal to negative pi over 4. Oh, theta, not theta bar. Theta is equal to negative pi over 4. Theta bar is the angle that we need to move back up to the positive x-axis, right? So what would that theta bar be? Yeah, if that was negative pi over 4, that's just got to be pi over 4, right? So theta bar is going to be 45 degrees. Okay? Now, if I do this, maybe I'm a person now using that second approach. Maybe we redraw that theta bar in the first quadrant. Say, okay, if that's a 45-degree angle, I'm going to redraw the reference angle in the first quadrant. If that's 45. Isn't that n? I'm going to let n be 1. Isn't that n? And then this would be n rounded to 2, so 1 rounded to 2. Is that okay? And now I can choose 1. I chose 1. You can choose 2. You can choose 3. You can choose 4. Whatever you want n to be. Or you can just leave it as n. But when I want to find the cosine of this thing, the cosine of 45 degrees, or pi over 4, okay, is going to be adjacent divided by hypotenuse, right? Okay? So we're looking here as that thing being radical 2 over 2. So I'm going to take adjacent divided by hypotenuse is 1 over root 2, right? And when you rationalize that, you get that radical 2 over 2. Okay? Now, let's just pay attention. Cosine in the fourth quadrant is what kind of number? Positive. Okay? If I look at that right triangle right there, that's a positive number, right? Hypotenuse is always going to be a positive number. So adjacent divided by hypotenuse is positive. Radical 2 over 2 is already positive, right? So cosine of negative pi over 4 is the same thing as root 2 over 2. If you were to type in cosine of negative pi over 4, you're going to get back 0.707. It's going to be positive. Okay? Now, is that the answer I'm looking for? No, I want a secant, right? So how do cosine and secant relate? Reciprocals, okay? So 1 over cosine of negative pi over 4 is actually secant of negative pi over 4, right? Well, then if that's the case, and I've got 1 over root 2 over 2, and 1 divided by root 2 over 2, you take the root 2 over 2, you invert it, right? Find its reciprocal, and multiply by the 1. So ultimately, you're probably not going to write all this stuff down, but when you found the cosine to be that ratio, the reciprocal, the secant, is the reciprocal of that. So it's 2 over radical 2, right? Okay? So the reciprocal is 2 over radical 2, which rationalizes it to 2 radical 2 over 2, which just gives me radical 2. So if I type in, go ahead and do it. Let's go 1 divided by cosine on your calculator. 1 divided by cosine. And then as the angle, type in negative pi over 4. Make sure you're in what mode? Radians. So one divided by cosine negative pi over 4 gives me that number right there. And hopefully, maybe we've seen it enough in our lifetime that we know that's square root 2. Type in square root 2 on your calculator, you get back that number. Okay. Is that all right? Keep working on that 5-3 assignment. Hopefully, and I'm going to push the due date back on that even further.